Dr. S. Swami. He has done, he is from Swinburne University of Technology, Melbourne in Australia. He is Associate Professor and Director of Transport Innovation Center and Air Program Leader. He has done his ME in Computer Integrated Manufacturing, PhD from Swinburne University. He has 15 years of R&D experience, 8 years leadership, leading defense air platform program, currently working with Malaysian automotive industry, or 50 publications he has to his credit in the last 10 years. Over to you.
Thanks for your kind introduction, please. I got it. Once again, thanks for the kind introduction, and also I thank the organizer for inviting to talk at this session on additive manufacturing. And I also thank all the speakers before me, all talked about the advantages of the additive manufacturing and amazing application and where it can be used. So I'm going to give you a completely different perspective of it. So probably, I think you might have a lot more questions to ask about the challenges in this. Before I start my presentation, I had past couple of days, I had been asked a couple of questions, completely not related to this particular topic. So I want to address those two questions. First question was asked, where is Swinburne and why I'm at Swinburne University? To address that question, I think most of you know this place, Melbourne Cricket Ground. Even if you've not seen personally, you might have seen in the TVs during the Boxing Day test match. That's the reason I went 18 years ago to watch the test match in MCG, but still I'm here in Australia. Interestingly, Swinburne is not far from there. That's one of the reasons I've been there close to MCG. Next question, what I was asked was about Australia. Many of the key people here not been visited Australia. So I would like to invite to Australia by saying that we have most of the most deadliest creatures in the world, like this. And also the smallest spider, which is the deadliest spider, and great white shark, and also the great reptiles like this. These are the deadliest creatures in the world. But saying that, in Australia, most of the animals are the northern part of Australia. That's where I don't live, because those deadly creatures are there. So I live in the southern part, that is in Melbourne. So this is where the Swinburne University is there. So I am in a safer place. So you're all welcome to visit my place there. And also you have quite cute koalas, kangaroos, wombat, and also cute little penguins also over there. So you're most welcome to visit Melbourne at any time. So going to the topic, before going to the topic again, I would like to address where I work. I've been part of the Swinburne University. I work in a factory of future. That's a new facility that has been established by the university. My area of focus in advanced inspection and manufacturing. So what you can, I couldn't get the pointer out, but you can see at the bottom corner, that's the additive manufacturing equipment, and also you can see laser ultrasonic advanced entity testing equipments also at the bottom. So in this presentation, I would like to go through, focus mainly on SLM process, the selective laser melting, and focus on the powder morphology, the issues with the powder, scanning strategy or the process optimization, and non-destructive testing, briefly talk about the issues with the non-destructive testing, and I'll finally summarize. Again, all the speakers before me talked about different process types: selective laser melting, electron beam melting, direct metal deposition, and also laser wire deposition. So there are 4 major types of the additive manufacturing process of there. Again, they also talked about advantages and disadvantages. So I don't want to repeat that again. So since my focus is on selective laser melting process, I would like to just briefly mention about the process again. As you can see, you got a CAD file or STL file that is input to the machine. Then you will get an end product, exactly what you got. I think that's still few more. This is the process without support structure. The product doesn't show the support structure. But you can see at the bottom how the process works. You've got 2 stages. One stage goes down as the build layer, and the other layer is the other part is the powder, where the powder is stored, and the powder is pushed through the roller onto the build stage. as I mentioned earlier, the process parameters are key, critical things. Again, there's a number of parameters. I just got only few of them, critical ones here. That's process-based, laser-based, machine-based, and also machine parameters with quite a number of machine parameters are there. To get the output, obviously, you're looking at high density and mechanical strength, and you're looking for dimensional accuracy and also good surface finish. Those are the critical areas. Again, the physical phenomena involved in the selective laser melting process are rapid thermal input and high solidification rate and phase transformations. Of all the parameters, laser power and scan speed directly influence the microstructures. So what I focus in this presentations are only few of them. So I'll talk about the powder particle size, I'll talk about the scan strategy, I'll talk about the defocus distance, and also part orientation. I think the question was asked earlier about the orientation, so I'll try to address some of the issues there, and also the scan speed. So these are some of the areas I would like to talk about today. So this is I'm not sure whether you can see clearly. This is what you look inside the bed of the manufactured SLM machine. You can see the powders on top of the component which has been built at the time, and it's all submerged within the powder bed. So you can see the powder particles close to the actual built component. So the key thing is, I'll talk about this a little bit later. Just look into the slide and I'll talk about it a little bit later. So when I talk about the powder morphology, in this particular case, I'm talking about 17.4 pH material. So obviously, when we get a powder, that ranges from 20 to 45 microns range. But it's not evenly distributed. That's the critical thing. I just try to show you different size, 20 microns, 30 microns, or 45 microns. That's how it might look like. So if I want to build layer by layer, 40 or 30 micron layer, so I have to move the stage 30 or 40 micron layer by layer. But if I got a 45 micron powder size, particle size, obviously it's going to hinder my process. The best way to do is, you can sieve the powder. That means you can grade the grain size within that particular range and work within the particular range. But the challenge is, once you start recycling the powder, that's where it gets difficult, because the powder particles tends to amalgamate or tend to stay together. That's what I was showing in the previous slide. When you look at that, when the part is made, there are powder particles embedded or next to the part itself. So whichever the particles next to it, obviously when you recycle the powder particle, already the size has grown in the size. So it won't be 20 microns anymore, it won't be 30 microns. Just to show you what difference it makes, even though it's not a nice image, you can see the 20 microns, if I put 4 layers, this is the height. 30 microns, obviously this will be the height after 4 layers, and 45 microns. You can see the massive difference. So what will happen if you have a different particle size when you're manufacturing? Surely you cannot have only 20 micron size. It will be very highly impossible to get only 20 micron particle size to manufacture a particular component, or 30 or 20, 45. So you will have a distribution. So you have to manage to play with the distribution. So that's the biggest challenge, one of the challenge that additive manufacturing faces. Just to show you an example what we faced when we recycled the powder. In this particular case, you can see the parts, tensile samples we prepared. It opened up, obviously, because again the powder particle size was different. You can see I'm not sure whether you can see it clearly again. Yeah, you can see it there, here, and also here. That's what the surface couldn't close properly, because even though we started building it, we didn't stop building it. We should have stopped it there, but we kept building the part. And you can see when the stage goes down, when the powder particle size is not uniform, obviously you have issues like this. And next one is the scan strategy. Unfortunately, I cannot show the strategy what we have used here, but I just can talk about it briefly. In this case, you're looking at a CT scan image. So conventional step-by-step scan can be done. The raster scan, go in a line, step up, another line, step up, another line. So you can do a raster scan. The conventional strategy compared with the multi-zone strategy which we have used. Again, I'm not sure you can visualize here. There's a porosity in the CT scan image here. Compared to the multi-zone, we didn't get any porosity compared to that. So scan strategy also plays an important role. How do you scan the laser when you melt the powder particle? within a part. When you look at the top surface of the same sample in a same image, you can closely look at it here again. This particular section, that is the end section of the sample, you can see porosities after each scan. Layer by layer, you can see there's a porosities there. It's not properly melted. The powder particle is not properly melted. When you compare to multi-zone here, the end section, you don't see any porosities in this particular case. So that's what you have to optimize the scan strategy for the powder particle type and the component you want to manufacture. Again, this is a CT scan with a dimensional variation, which shows multi-zone part looks far better than the conventional scan type. Again, this is a different sample. This is an effect of scanning speed, how fast the laser moves on top of the powder. So I'm talking about scanning speed, and I'm talking about aluminum silicon 12 powder here. As you all know, aluminum has a high reflectivity, so that means you need higher power to absorb the laser heat to go into the melting the powder. Obviously, if you go faster, not much is absorbed by the powder particle. That's why you can see with a higher or faster scanning speed, you have a lot of porosities in the samples on your left, and on the samples on your right, you can see with the shorter scanning speed or slower scanning speed, you have a really very high dense parts. Again, even with the lower scanning speed or slower scanning speed, combined with the scanning strategy, if you do the conventional scanning strategy, you can see the porosities here. The density is roughly around 99.5. At the same time, when you do the multi-zone scanning strategy along with the source speed, you'll get 99.95 per very, very close to full dense part, which is really good. That's what most of the people are looking at, especially the machine manufacturers and also the people who are working in the aerospace and defense application. The another parameter I want to talk about is the defocus distance. This is where the defocus distance is basically where the scan or the laser power is focused at. As you can see, in this particular case, the negative focus, that means this is the layer where the powder is, but the focal point is obviously at the -4, it's under the surface, because the heat intensity will be more, it won't disperse after that. And again, you can see the other one is the positive defocal length. What we found is, particularly in our experiments, we found -4 defocal length is good. Again, this will change depending on what size of particles you're using and what's the average particle size. That will determine. We had a trouble with recycled powder. When you have a fresh powder, when you use -4 defocal length, all perfect. But when you recycle the powder quite often, then you have to change the parameters. So that's where, again, the challenge is there. When do you change that particular parameter? And again, you're changing the properties of the component, which is very hard to know. So it's very, again, that's why quite a lot of research is happening in this particular area also, mainly trying to optimize those conditions so that you can achieve a consistent properties along the component. This image just shows the surface roughness values which we try to measure on a component. So build orientation. Again, somebody asked earlier about the build orientation. As you know, all the parts are not just flat, horizontal. It has vertical columns, you have inclined columns, so you have different shapes. As you can see in this particular component, just a lever bracket. The same bracket, I think topology optimization, as Nayan Patel mentioned earlier, you can see optimize the component into different dimensions or different shape, which can be only produced through additive manufacturing process. And also, you can see hollow structures inside that particular component, which like a truss kind of thing, which is only possible through additive manufacturing. It cannot be done by any other process. So that's significant advantages there. But however, the challenge is again with regard to the inclined or horizontal or vertical columns. What is the variation? What are the property variations are there? So that is a bit interesting to look at the research point of the view. Particularly in that case, quite a number of studies has been done by a lot of people, researchers around the world, focusing on different properties on horizontal build, vertical and inclined build. As again, you can see compared to the rod sample, which is in the end data, but compared to the horizontal, vertical and 45-degree, we have completely different parameters. Having consistently obtained this kind of information is very, very important to know which is the best property based on your product what you want to use. So whether you want to build it horizontally, vertically, it all depends on the end product, where it's going to be used and applied. Again, another example from the literature. You can see at the bottom, mainly I'm focusing on the bottom graph. So this is a completely different process on titanium alloys, selective laser sintering, melting process, direct metal deposition process. In this particular case, again, you can see at the bottom graph, so as built horizontal and vertical, there's a significant difference in the properties compared to the machine samples, which is almost consistent. When you do vertical or horizontal, doesn't matter, it is consistent compared to the vertical and horizontal build. Obviously, each treated samples has a similar condition. If you do it in a similar condition, then obviously you gain the properties there. But as such, when you build it, obviously there's a difference in the properties. Again, another advantages of the additive manufacturing is, again, you can manufacture different lattice structures, different shapes and forms, so that you can reduce the weight. That's the whole idea of additive manufacturing process. But saying that, we did simple the 3-point bend test. The whole idea of this particular test is just to see how the process has been optimized, what are the issues are there. Again, when you look at this particular sample here, the triangle shape, and especially when the process is not optimized, the line of cracks, initiation, or where deformation starts at the porosities, where the porosities are. So it's very critical to optimize those conditions to achieve full dense part. If you don't have it, obviously, the structure will fail straight away. So this is one of the example. Obviously, you can say that, why don't you do simulation? Yes, that's a good idea. But when you start simulation, you cannot use simple rot sample data. The properties of rot samples cannot be used here. So you have to generate your own data through SLM process. That particular powder morphology, that particular powder type, whether it's vertical build, horizontal build, or inclined shape. So you have to generate your data. Then use that particular data for the simulation purpose. We tried with normal condition, that is rot data, and it was not comparable with what we did with additive manufacturing samples. So you have to input the data that are obtained for specifically for that particular material, that particular powder type, and build orientation, or also the shape. So that's why it's critical. Before you start doing any simulation work, you need to build the material database. Obviously, you can get it from the suppliers, but again, you might need to optimize for your own conditions. When you change any parameter, then obviously you have to optimize, or you have to generate the data for yourself. That is critical. But you should normally get generic data from your suppliers. They will provide that information about that. But once you want to optimize for particular conditions, then you have to generate that data, which is a challenging task in itself when you change multiple properties or multiple parameters. So finally, obviously, this most important one is, again, NDT. That has been mentioned earlier by Srinivas and other people, talking about the challenges in this is additive manufacturing processes, the NDT qualification that needs to be done at the end of the product, especially if it is going to be a aerospace or defense or structural critical components. Most of the examples that's been previously shown were not structural critical components. So far, the structural critical component is very, very important to have this kind of NDT methods. So you have a number of inspection methods: C-scan, tomography, and eddy current, thermography, and laser ultrasonic testing. Just in the next slide, I'll show you. Obviously, just briefly, it would be nice to have an online inspection system, but unfortunately, with the high temperature condition in the manufacturing process, it might not be that easy. But it would be nice to have something on online inspection system. So in this slide, just I made some comparison between different inspection processes. What would be a likely scenario where you can use it? Most of the time now, tomography is being used because you get a lot more information, which is very helpful. Obviously, you can see cost-wise, obviously it's high, but speed of inspection is comparatively high, resolution is high, and the depth of information is high. Unfortunately, it can be used in the high temperature conditions. But however, in laser ultrasonics, you get a lot of information. Cost compared to tomography, it's cheaper. For example, if a tomography machine costs $1 million, laser ultrasonic machine will cost you around $200,000. So it's 1/5 of the cost. But only problem is you may not have the information what you get from tomography, but it can be applicable in high temperature application. So when the part comes out with high temperature, if you get a high temperature part, especially direct metal deposition, it can be used in that particular case. So this is some examples we done work with IATM Chennai. So this the tomography work on additive manufacturing samples. As you can see, obviously we didn't optimize the process. You can see a lot of porosities there. This is two small simulated holes with 2 millimeters. And the same thing it was done with immersion C-scan. Again, the challenges with the porosity, you can see that so much with different frequencies, the intensity is varying, so you lose a lot of signal with the porosity. So finally, to summarize, obviously there are significant advantages for additive manufacturing process. There is no question about that. But the challenges, what I mentioned, are key things: process optimization, especially looking at the scanning speed, scanning strategy, and also looking at the defocal length or the critical parameters to look at. And also powder particle size. Still, as you can say, the people, manufacturers and suppliers of the powders, they can say, obviously you can use for a number of times. There are certain limitations there. So you have to find your own constraints within the powder recycling process. You have to identify how long you can use the powder depending on the parameters you are using. So that's the other challenge you have to identify yourself. And obviously, the build orientation is the other factor which has to be looked at, because depending on the part, what you're looking at and where it's going to be applied, that will determine the build orientation. So that will determine the properties, what you want to look. And obviously, the cost has been mentioned by all the presenters, so which is a critical parameter also when you decide what to do with conventional or additive manufacturing. But again, additive manufacturing has own advantages. Again, the parts that can be specifically manufactured by additive manufacturing has a significant advantage over other conventional process. So that's where additive manufacturing is going really useful. But if you can address these challenges, then surely significant progress can be done. Thank you. And I'd like to acknowledge my colleagues and partners in the presentation what I've given today. Thank you.
If there are questions, I'll permit two to start with. I must say that when I took over as a session chair, I was wondering 5 papers in one session on the same subject. But I think each one of them has been able to give us a different facet or different angle to look at the same technology.
I know you will be asking the question. I'm waiting for it.
Thank you, sir. And it was really interesting topic. My question is related to the process actually. One of the challenges that we face down the line is when we are deciding the support structures. Many a time the critical component does not permit us to define the locations. So I want to know from your perspective, what is the basic principles on which do I need to change the location of support structures?
I think it's better to ask the equipment manufacturers, because they are the ones, its support structure usually determined when you generate the STL file, obviously convert into slices. It's automatically the machine parameters identifies which are the critical areas. That will automatically show you where are the support structures. And then you can play with it slightly. You can modify according to your needs. You can change the support structure height or width. You can do that. But most predominantly, initial part of the work is done by the mission program itself.
True, sir. True, yeah. I understand. For example, in blade aerofoils, particularly towards the tip region, we cannot put the supported structures. So if I need to change the location, what should be the basic principle on which I should relocate the location?
In this case, minimum support structure is always the best option to go for. But saying that, you have to change the orientation. You have to play around the orientation where, again, somebody showed about a hole. How to build a hole if you want to have support structures in between the holes, okay, which is not a good thing. You will have a lot of support structure materials, wastage will be happening. So it is better to build it horizontal instead of vertical, doing the same thing. So that's where you have to play around the build orientation, how to build the part. So that will determine the minimizing the support structure. I'm not sure you answered the question, but minimizing
okay.
Yeah.
And then coming to the next question, sir, regarding the acceptance criteria for the parts. What do you prefer, to go for radiography or for CT scanning? In precise, like you have the constraint of the equipments in for non-destructive testing.
That's true, because still there is no standard process yet for additive manufacturing. Tomography gives far more information, but the voxel size, that is the smallest resolution you could go for, that will take, say, 8 to 10 hours or 15 hours time, depending on the component size. So it will take a long time to inspect small parts also. If you got a large part, then it might take days to do a tomography. that gives a lot of information. But saying that laser ultrasound or ultrasonic system, which is cost effective or small, or the price wise, it can give still the same information, but you may not be able to do the full scan of the part. That's the only challenge. You might have to identify the critical areas,
Yes.
then focus on the critical areas, then that's where you can able to do inspection on that.
Thank you, sir. Thank you so much.
Very good presentation, sir, indeed.
Thank you.
I would like to know, like the conventional metallurgy, the structure or microstructure part of it, be it for a 17.4 pH steel or a titanium alpha beta structure or a nickel based superalloy gamma gamma prime structure. How does the metallurgy of conventional parts or structure differ from the additive part, and what efforts goes into during heaping or heat treatment, wherein the refinement is made to see that the properties, both strength as well as ductility, comes or meets to the conventional or is better than that?
I think already in the literature, based on the literature, what has been done, so we have not done much work in that area. We are progressing in that area. As based on the literature, obviously the tensile property looks far more better. Again, percentage of elongation is not that good in most of the additive manufacturing process. That's why the heat treatment is done to improve the process. But saying that, again, different orientation, different parameters plays a major role in that. So optimizing the condition for your particular application, which is critical. So that's a lot of groundwork has to be done. That's where the challenge of additive manufacturing is. A lot of groundwork has to be done for a particular component before it goes into full production.
Yeah, thank you.
And that is to felicitate all our speakers. To start with, Mr. Suresh. That's all right.
Trading and carbonite trading, and we have a number of specialists here, starting with the Bhishma Pitama of heat treatment, Dr. Zoltan. We have 4 papers here, Dr. Zoltan, then Dr. Santosh Usmani. Usmani is here? Yeah, okay. I think Mr. Jaroslav's paper is replaced by some other gentleman. Yeah. And finally, Professor Sai Ramudu. Yeah, he's also here. To conduct this session, I'm sure you will expect somebody from the heat treatment line, and we have a very able person in that, Mr. Sandeep Rege, who handles the heat treatment section for Mahindra and Mahindra. The user, he can pose very, very critical questions to all the speakers. So I hand over this session to Mr. Sandeep Rege, who is also our organizing committee colleague. He has had, I think, more than 12 years of experience in Mahindras as in charge of heat treatment section for auto division. Mr. Sandeep Rege, please.
Can I now call up on stage Bhishma Pitama, Dr. Zoltan, please. Dr. Okay. Dr. Hosmani. Yeah, don't mind.
I was one of the
Professor Ramduta and yeah, Siko Warwick. all those eminent speakers, they have wide experience in nitriding and carbonitriding. So we can hear from them, and you can pose a lot of questions to them. The many users I can see here. And let's now start with Mr. Zoltan, Dr. Zoltan. Okay, he is PhD, and he has more than 60 years of experience in this field. He is from Romania, University of Romania, and he has done PhD in material sciences. He is basically a mechanical engineer, and then he has done PhD in material science. So over to Zoltan. Please.
Thank you very much. So we'll start with
This one, no, sir?
Well, good morning, everybody. First of all, I think that I should nitride my voice a little bit just to be hard enough to can be heard. Well, I will do my best, but certainly I am at your disposal to ask me after the meeting whatever you want in this field. I was named by Professor Tom Bell as a nitrogen man, dealing most of my life with nitrogen. So, well, what I intend to do, don't expect me to give too much of theory, because either we know very well the theory or we don't know at all, because there are a couple of things which are still not elucidated in plasma nitriding, especially when we talk about auxiliary cathode or about active screen. So all the theoretical phenomena are not yet completely clear. So what I intend to do is just to give a few ideas on the possibility and a technology which is widespread but still has a lot of room for innovation and for further development. Well, first of all, I should emphasize a few facts at the beginning of the last century, because that's important. So whatever we do in technology, we have to consider what was the progress in science, and this progress was fantastic, and certainly the progress in science and provoked this, progress in technology as well. There's no doubt that the last century was the century of physics. So beginning from the theory was Einstein, and from the theories of quantum mechanics and so on and so on. And all this development was completed at the end of the century by a fantastic, incredible development of data processing and data transmission, which is today probably one of the forerunners of the science and technology. And certainly all this development in science determined also strong development in technology as well. So this is absolutely clear. What are we doing? So surface engineering is my specialty. And the company I represent, the Plasma Term, is dealing with surface engineering. Once we named thermochemical treatments, we now say surface engineering is a little bit more expressive. For more than 40 years. What is typical, and is also you will see in my presentation, is small size engineering components. So what we were doing all our life, that was to concentrate on the small size precision engineering components, first of all for textile machines, high-speed sewing machines, and actually I must tell you that is very interesting. I think that after the weapons, the most intensive wear and fatigue, surface fatigue problems are in textile machines. A high-speed sewing machine, for instance, which is running at 20,000 a minute, up to 20,000 a minute, and stops 20 times a minute, you can imagine what kind of solicitation appears. So that was our task, to try to find wear-resistant layer, to try to find technologies to make a high wear resistance. So that's Plasma Term. Well, the nitriding nitrocarburizing was on the center of the world because of two basic properties. First of all, you have a very wide range of properties, functional process parameters, and you can also apply the process for a very wide range of materials which respond positively. So you don't have to have only high alloys or whatever. So you can have plain carbon steels and up to tool steels. You can obtain, certainly changing the process parameters, you can obtain very good properties. So, and the result of treatment, as you very well known, is an increased wear resistance and improved corrosion behavior associated with increased resistance to surface fatigue. This is also very important because in precision mechanical parts, surface fatigue is many times one of the determining cause of failure. So, I think even if it's well known, it's just useful to make a few, to remind a few things on nitriding, nitrocarburizing. First of all, it's very important that the layers show W character, because we have a conventional diffusion layer, which is well known, of nitrides and nitrides of the iron and nitrides of the alloying elements. And then, which is very important, we have a compound layer which has a ceramic character. That's why we usually, many times we say, is a ceramic conversion process, because we obtain a ceramic character of the compound layer. Well, with a slight exaggeration, we might say the result is a duplex layer. Well, usually we do not say a duplex layer for such kind of layers, but it is a little bit like a duplex layer. I gave just a schematic presentation. Well, another particularity of the process is, as we well know, that is in ferritic stage. So it's ferritic carbon nitrocarburizing, which means no ferrite austenite or ferrite austenite martensite transformation, which is extremely important for highly complicated, sophisticated parts, because no deformation appears, or the deformation is very rare. I should make here a parenthesis. Many times people come to us to make a treatment because it has no deformation. The first question, what is the history of the part? Because indeed we have no deformation after nitriding, nitrocarburizing, presuming the preliminary heat treatment was correct, and so the history of the material is correct. That's very important. So we always know that there is a slight increase in dimensions, especially when we make nitrocarburizing, but this increase usually, even in the precision mechanical industry, doesn't play any role or doesn't make any problem. So what I should like to emphasize very much that there is, when we talk about nitriding, we can talk about nitriding just with two different procedures. One of the gases and the other is plasma. When we say liquid nitriding, that's not correct, because in salt baths we do not make nitriding, we make nitrocarburizing. So this is very important, because many times in industrial applications, this is this kind of confusion. So that's why I made this small presentation, that nitriding is gases or plasma, and nitrocarburizing gases, salt baths or plasma. I must tell you that I am very much fan of the salt bath nitriding, but unfortunately, due to the environmental regulations, we had to replace salt bath nitrocarburizing with other procedures, gases or plasma, which certainly work, are very good, but still in many application areas, salt bath has big advantage, but we have to forget about for the moment. Well, I just have shown a couple of pictures, which is for the nitrided structures. Down here you have an electron microscopic picture which shows the nitride needles. This is well known, so I just put it just to remind you about this. And when you talk about nitrocarburizing, so I have also shown the compound layer, which I should like to emphasize one thing with the compound layer. There are many discussions which should be the ideal porosity of the compound layer. Should it be porous or not? Well, on my experience, a certain porosity for different application areas is extremely important. For instance, once again back to the textile machines, that's very important because in many cases you have a boundary lubrication, which means no hydrodynamic lubrication is possible, and in this case the porosity of the compound layer plays an important role because it will enhance the wear resistance. It's also, we have now a very interesting application. We are working in a consortium for an EU project managed by the Imperial College in London, where my task was to solve the problem of the wear of tool. It's alloyed cast iron. Well, we now obtained a very good nitrocarburized layer, good compound layer with a controlled porosity. And what we are doing now, and maybe somebody can help me in this respect, to introduce nanographite into the pores, because then is the lubrication, which just to say that this is for deformation of aluminum, and the aluminum does not accept any kind of liquid lubricant for deformation. But I think, and this theoretically should be correct, that introducing nanographite into the pores of the compound layer is a possibility to obtain a good wear resistance. We see. Well, there are just a couple of examples of different steels, nitrocarburized, because we do probably about 70–80% of the treatments is nitrocarburizing what we do, and then the rest is nitriding. Well, certainly this is also well known that in this respect also we have to be very clear that the diffusion layer certainly does not change the structure in the diffusion layer. It's a strengthening through precipitation, the precipitation of the carbides of the alloying elements. But in the compound layer, the alloying elements practically don't play any role, or their role is not significant. So this is very important. The last notice for stainless steels. We make a lot of plasma nitriding for austenitic stainless steels at low temperature, which means a temperature below 400 degrees centigrade, obtaining a supersaturated austenite, the so-called S phase, with very good results. And I think this is also one of the very important treatments. Well, we tried all the possible versions of nitriding, nitrocarburizing. We started with gaseous nitriding when it seems that we were the first to observe the role of oxygen in the nitriding as an activating medium. And then we made salt baths, and we are working now mostly on plasma. We built, the equipment was built by our company, and I hope now it will be introduced in India by our partners here. So this is, the plasma nitriding has a lot of advantages, a very good and close control, but the problem is usually the halo cathode effect and the edge effect. Certainly there are different versions, there are different technologies, different systems to try to avoid the edge effect and halo cathode effect. I won't speak about the pulse plasma nitriding because of different reasons. So it's pulse plasma nitriding tries to avoid these negative phenomena, and partly does. Well, we did not work in this respect, so I will concentrate also to the time problem, to the problem of using active screen, or even more, not exactly active screen as a nomination, but secondary cathode. Why do I say what is the difference? Is practically is no difference, but usually when we talk about active screen, we understand one type of system. When we talk about shared glow discharge or a secondary cathode, that's a little bit another thing. Well, we are mostly working with dissociated ammonia, so a hydrogen-nitrogen mixture. When we make nitrocarburizing, certainly we add methane, so not CO2, but methane for carbonizing media. Well, there is also, we have different procedures where we can add also CO2 or even low quantity of oxygen, because oxygen has an extremely important role in layer forming, not only because is increasing the surface activity, but also because it is enhancing the layer formation, and that's especially the epsilon type nitrides or carbon nitrides. Well, the active screen is eliminating, or partly is eliminating, the halo cathode effect and the edge effect. So this is the biggest drawbacks of plasma nitriding. So you have to be careful. How do you make your load, and how do you will form the process? Well, it's very interesting, and I should like to emphasize, we are talking a lot about the reaction kinetics in active screen. What must be very clear, that the reaction kinetics is a very complex phenomenon in active screen, and is not completely elucidated. There are different theories, just as I will show you. I will show you later. There are different theories. The pulse and sputtering theory of the University of Birmingham. Now Spies and his collective work with another theory. But basically, we must know that for the active screen or for the secondary cathode, the glow discharge, or the physical chemical phenomena behind are not completely elucidated, so we have to work on it. And we also try to do it. Well, I talked about the active screen, which means I will show you some of the drawings, what is the active screen. So the screen is at nominal, basically, the screen at nominal voltage, the parts at floating potential or at a bias voltage. What we also do, this is, let's say, a version of active screen. Both the screen and the load are the nominal potential. I should like to emphasize very much, this is only for small equipment, so not for laboratory equipment, but very special, small size equipment, small power, because we had a surprise. At the beginning, we just tried to make it, and we observed that this, how much time do I have? 5 minutes, okay. That's basically the difference between the active screen and the auxiliary cathode is that both the parts and the cathode, the auxiliary cathode, is at the same voltage. Certainly it sounds a little bit strange because it's increasing the energy consumption, that's right. But for small power equipment, what we observed, and I can prove it, no edge effect appears and no halo cathode effect. Why? We do not really know. That's something which we still have to be explained, because certainly what we know, that we modify the energy distribution between the cathode and the parts, and this is why. Well, just because of time, I will go a little bit further. So I will jump over these sketches, which we all are well known, of DC plasma nitriding and laboratory assembly of active screen plasma nitriding. So this is a comparison. And as I told you, the active screen, the secondary voltage is that we have the same potential on the parts and on the screen. Well, this is a equipment made by Jean-Georges in Luxembourg. They were with the first equipments for active screen plasma nitriding. And this is in my laboratories, where we have 4 furnaces of Nitrion type plasma nitriding units built by our company, and the arc discharge, glow discharge protection is our patent. Well, what I should emphasize because of the time, so a couple of applications which gave very good results. So we got from a company from Canada some filters, filter rods, you can see it better here, for steam plant, where you have to have both the shaft, the mantle, and some 500 holes of about 8 millimeter diameter in the mantle to have nitrided with a uniform layer. And I don't think that anybody can do it without an active screen or without a secondary cathode. We use a secondary cathode, so the shared glow discharge, and we obtained very good results. As you can see here, this is the micro hardness plot with a very high micro hardness. You have the steel there and everything. And if you compare just the structure, the left side, the structure is in the hose, and the right side on the mantle. So you see that the layer is very uniform in both the mantle and the hose. So we have some 12 different parts like this, and I don't talk much about this, but let's show you a rather unconventional load, because there are a lot of different small parts, even of different steels, in one single load with auxiliary cathode, so with short glow discharge, and we obtained really very stable results, and that's not once. We are producing it continuously, so it's a flexible contract heat treatment, I might say, and we obtained very good results. These are two steels, one of another is C35 steel with a compound layer, the other is a chromium molybdenum steel, which is well known for you. So what is important in such a very specific load? We did not have problems with the edge effect. So this is what we still have to elucidate, we still have to work, and we are working with some colleagues from Freiberg and even Birmingham, just to try to explain why is this advantage on this case of potential. Well, as in conclusion, so certainly nitriding, nitrocarburizing, I forgot to tell that was not nitriding but nitrocarburizing. So this, for all these parts we make nitrocarburizing, but it was written. Okay, so nitriding, nitrocarburizing may be performed with good service results as in very different treating media and for very different parts. That's, till now we have a kind of a record with more than 500 different parts, 500 type of different parts with very good results what we apply. And another thing, that an auxiliary cathode, so as we named the shared glow discharge, could work very well in conventional DC plasma nitriding units. Certainly it's recommended only for low power, because the energy need is increasing by about 20 to 25%. Thank you for your attention.
Thank you very much, Doctor. Any questions? Anybody? Okay. Yeah.
Hi.
It's on.
Hello. Yeah, I am Shashi Arora. Dr. Zoltan, can you just talk about the kind of industries which you experience, which you are feeling that, you know, these kind of systems can be used? What kind of industries you feel in the automobile sector or in the other sectors?
Well, what I advise for our type of equipment, there are very special built equipments, which means it's an equipment with large retort to be able to put single pieces of industrial application like long shaft, cylinders and so on, with low power, 15 or 30 kV. which means that you can apply practically for industrial experiments, and not only laboratory experiments, for industrial experiments, for very different parts, and certainly you can use for laboratory experiments as well, because you can make different adjustments which are suitable for laboratory experiments. We began at the, when we started with this program to use for laboratory experiments. Then later we are operating practically a contract heat treatment also with this these furnaces with very good results. I must tell you that it's one of the most beneficial activities of my company.
Thank you, Doctor. Thanks for your speech. We have had 60 years of experience, unfolded here. So have a good.
Thank you.
Please. Our next speaker for the day is Dr. Santosh Hosmani. He'll be speaking on surface alloying heat treatment of iron-based alloys. Dr. Hosmani has done PhD in nitriding from Max Planck Institute, Germany. He held various faculty positions as NITK, IIT Delhi, and COEP Pune, right?
Yeah.
Currently, he is a senior manager at KCTI Bharat Forge. Here is Dr. Hosmani for us.
Thank you. Okay, so good afternoon all. So actually initially I was supposed to speak on my fundamental research in nitriding. Then I later saw that list of speakers. I realized that there is a Dr. Sairam Meka. So he is also going to talk about it, and actually we work together in Max Planck Institute. So I thought that let us speak about my latest result. So actually I'm going to speak about the surface mechanical treatment, that means the effect of surface mechanical treatment on nitriding behavior. So that is a very interesting field because this is our latest work, and what we observed is quite interesting and fascinating. So that's why I decided to select this topic. So before I move further, I will briefly explain what is a SMAT. It is basically surface mechanical attrition treatment. What it involves a container. It's a vibrating container, and it consists of a hardened steel balls. It can be a ceramic steel ball. And at the top of it, you have the specimen, which is located here. Due to the vibration of the container, you have the continuous impact on the specimen surface. And this process is happening for a multiple times, and that will lead to a severe plastic deformation of a surface. You may think that this process is similar to the short pinning, but fundamentally this process is different from a short pinning. In short pinning, you have a different shot size. Your shots can be irregular in size, as well as the velocity of shot can be different. So in short, the short pinning process and SMAT, they are fundamentally different from each other. So what is happening here in the case of SMAT? In case of SMAT, you have accumulation of strain at the specimen surface, and that strain is gradually decreasing as you move inside the specimen surface. That means that you have the continuous deformation, and due to this deformation, you have the formation of nanograins at the specimen surface. And these nanograin or crystallites are helping us in various different ways. What I'm going to focus is that how this nanograin formation is affecting the nitriding behavior. Before I do that, I need to explain a little bit about the SMAT process and how the smatting of a stainless steel is playing a role. So what we observed is that we started working on this topic for 4 years back, and what we observed is that literature, they are not mentioned specifically about the role of SMAT parameter. And what is the effect of that SMAT parameter on corrosion resistance, that is passivation behavior of stainless steel, and how that passivation behavior is playing or interfering into the nitriding process. So that's why we selected this topic. So what we have, actually due to the time constraint, I'm not going to speak about all those 3 topics, but I'm going to focus on first 2 topics. The SMAT setup, what exactly is that you have the vibrating bottom plate, this vibrating bottom plate, and you have the spheres, hardened balls are there, and they're continuously hitting on the specimen surface. And that vibration can be given by the mechanical means or electromagnetic vibration can be given. We have fabricated this setup in our laboratory, and we have given the electromagnetic vibration to the bottom plate. So here it is important to know the velocity of a ball. This velocity of ball is very much dependent upon a size of a ball. Because ultimately, depending upon the size of a ball, you have a different kinetic energy stored in the specimen, At the same time, this velocity will decide how many times your specimen surface is going to be impacted by the vibrating ball. So in short, this MET parameter, if you really want to understand, there are multiple factors, and these multiple factors should able to give some kind of a conclusive thing which will help the microstructure evolution in the material. So what exactly we are going to see? Now we'll see the 304. You know that this is basically austenitic stainless steel. And what SMAT parameters are there? The ball size, you have the SMAT duration, the gap between the specimen surface and as well as the bottom plate, and as well as the number of balls. So here, for the simplicity, I'm using the term that percentage of coverage of the chamber. That means if you have the 25% cover, that means the bottom plate of my chamber is occupied, 25% of the space is occupied by the balls, then like 50% and then 75%. So that is the meaning of this. Now in short, we have given the three important set of experiment. In one case, we have varied the SMAT time. In other case, we have varied the SMAT as well as the size of a ball, and we also varied the percentage of balls into the chamber. I will not able to speak all those parameters, but briefly what I want to say is that here this microstructure, this is not like a badly prepared or metallographically prepared sample. It is not a scratches. These are all mechanical twins or deformation twins. These are generated due to the continuous impact by the balls. If you see this, these mechanical twins, they interact with each other, intersect with each other, and they converted to the rhombic block. They are of nanometer in size. So these rhombic blocks are playing important role in oxidation behavior of the material, that is the passivation ability and nitriding process. So at the same time, since it is an austenitic stainless steel, you know that there is the deformation induced transformation. That is called deformation induced mitocytic transformation. Here, since the process is a plastically deformation, there is a formation of martensite at the specimen surface. And this martensite quantity is very much dependent on the SMAT parameter. As you increase the SMAT duration, percentage of this martensite will increase. So obviously, because you have the continuous deformation which is happening, and this deformation induced martensite is dependent on strain rate and the amount of strain. As you increase the SMAT duration, amount of strain at the specimen surface keep on increasing. So in short, the percentage of martensite will keep on increasing with respect to time. Apart from that, for a constant SMAT duration, still it can be increased if you have more number of balls into the SMAT chamber. Because more number of the balls for a given time, the entire surface is impacted by more number of balls. That means you have the pinning intensity. This is a new term what we introduced, which is quite effective in explain the qualitatively the amount of strain at the specimen surface. So I will not go into the theoretical aspect of this. So here you can see that we have the two set of microstructures that are shown here. One is with the 3 mm diameter ball, another is 8 mm diameter ball. And as well as percentage of ball are changing from 25% to 50% to 75%. If you see here, as I move from this end to other end, the number of ball increases. At the same time, for a same percentage of ball, if I change the diameter from larger diameter to smaller diameter, the number of balls are again changing. Even though percentage of area is at 25%. What does that mean? That means that as you increase the number of balls, the amount of deformation of the specimen increases. How I can prove that? If you see here, if you see from this image to last image, if you see from the 25% and 75% ball, you can see the contrast into the etching contrast. You can see that the 25% you can still see something in there. However, in the 75% ball, you can't see anything. Even though we applied the same etchant for a same duration. What does that mean? That means the surface is attacked more by the etchant. That means I have the more mechanical twins in the specimen surface. At the same time, the spacing between the mechanical twin also increases. What does that mean? It means that the amount of deformation at the specimen surface increases as the number of ball increases. And that is playing a role in amount of martensite quantity in the specimen surface. Now how you explain? There are plenty of things are there. That means that I have a different impact if I change the gap between specimen surface and the bottom plate. As well as the number of ball is another constraint. Then SMAT duration is another constraint. So I have plenty of variables are there. How I can explain all those variables into single term? That is by using a pinning intensity. So that is a major contribution by us into this particular phenomena. So pinning intensity, what does that mean? It means that you consider specimen surface. Initially it was like this, like for example figure A. How much time is required to cover the entire surface by the indentation marks, which are shown here. That is the spherical marks are nothing but a deformation deformation region which is observed on the specimen surface. So that means that this time which is required to cover the entire surface divided by what? The SMAT duration. So that will give the terminology called pinning intensity. That means that pinning intensity tells you how many times your surface is impacted by ball during a SMAT duration. That is the pinning intensity will tell you. We got a perfect correlation between pinning intensity and quantity of martensite. Here you can see that as I increase the percentage of ball, my pinning intensity is also increases, which is shown by the blue color line. So pinning intensity increases. At the same time, quantity of martensite is also increases. So as I mentioned, martensite quantity is very much dependent on amount of strain. So as I increase the ball, increase the PI, strain is increased. So that's why martensite quantity increases. However, if you see at the lower percentage of ball, you see the reverse trend. What does that mean? Even though my pinning intensity is more for the case of 3 mm diameter ball, but still the martensite quantity is lower. Why that is so? Because there is another term which comes into the picture, that is the strain rate. So you have the higher strain rate when only the small quantity of your space in the chamber is occupied by the ball. So you have the very large velocity, less collision between the ball is there. So you have the high strain rate. So higher is the strain rate, you have the adiabatic hitting is there. And because of that adiabatic hitting, you have the lower percentage of martensite quantity. Anyway, so these are all related to the martensite quantity. Now our session is related to the nitriding. So I'm more interested to talk about nitriding now. So these are just conclusion for this part 1. Now, what we observed is that due to this different SMAT parameter, your corrosion or passivation behavior of the specimen is different. And when we do the nitriding, you know that in case of nitriding, you have the two processes are there. One is the sputter cleaning, which will clean the surface, any kind of a contamination as well as oxide which is there. And second is a plasma nitriding process. What is the duration for sputter cleaning? What is the duration of nitriding time? It is, people rarely mention about for what duration I have to do my sputter clean the process. So that means that if you do the less sputter clean, if your material is more passivation tendency due to this plastic deformation, then your nitriding process, in your nitriding process, your actual nitriding time is reduced because some duration is consumed to do the sputter clean, which is not happened in the earlier step. So, okay, so first I will show you about the corrosion results. So what we observed, here you can see that the bottom line is for the non-smatted specimen. As you do the smatting, you have the open circuit potential, its value increased, it is shifted to the upward. That means that your corrosion behavior is now improved. That means your corrosion property is improved. Again, if you, in the SMAT process, you have the quite of surface becomes rough. That roughness is about 0.5 micron to 1 micron. You remove that surface roughness and you observe the open circuit potential. What it says that your corrosion property is further enhanced. That is by your S2P. That means the polished. P indicates the polished sample. So polished sample has a better corrosion property there. There is another proof from that. Another proof what it says that as per the Nyquist plot, larger is the radius of this particular plot. It indicates that you have the better corrosion property. So what it observed? It shows that you have the S2P sample. S2 indicates the smatting condition and NS indicates the non-smatting condition. So non-smatted specimen has the lowest corrosion behavior. However, the S2P has a better or superior corrosion behavior. That means the passive film is quite stable there.
Dr. Osmani, 5 more minutes.
Yeah, I'll just wind up that. So as I mentioned here, the plasma nitriding consists of 2 steps. One is the chemical cleaning duration and other is the plasma nitriding duration. That chemical cleaning can be done by using hydrogen or argon atmosphere. We did hydrogen atmosphere there. Now what our hypothesis? Our hypothesis is that if my passivation behavior is increased due to the surface deformation and if I am not choosing the appropriate sputter clean duration, then my nitriding duration is consumed there. In short, my effective nitriding time is reduced. That is my hypothesis, which I have to prove that. How I prove that? Intentionally we select 2 sets of experiment. In one experiment we selected the lower sputter clean duration, other case higher sputter clean duration, that is 30 minutes and 120 minutes. What is the effect of that? Effect of that is that this set of experiment is N1, that is a lower sputter clean duration, other is the higher sputter clean duration. In all cases, you got the higher case depth compared to the lower sputter time. Even though my plasma nitrogen duration was same entirely, everything was same, only sputter cleaning duration was different. And that drastically affected my nitrided layer thickness. There is another proof for that. The GDOS, it gives the nitrogen concentration depth profile. You can see that the red one is supposed to the N2 cycle. That is a higher sputter clean duration. So higher is the sputter clean duration, I got the deeper case depth. So that means that another thing is that you got a higher surface nitrogen content. So all those results which confirms that we have the influence on sputter duration on the plasma nitrating duration. And why it is affected? Because of surface deformation. So that's why whenever your surface is subjected to any kind of a grinding or any kind of a machining operation, then you should carefully select your plasma nitrating parameter, because that significantly affect your case depth. So that is what I want to explain here. Another thing is that in this case you got a expanded austenite, as I mentioned by my previous speaker, that in case of a stainless steel you got an expanded austenite, and this expanded austenite is again decomposed into stable phases, that is a chromium nitride formation or ferrite formation at later duration. And there is another indication for that in case of XRD. In case of N2 sample, we got the X-ray diffraction peak due to the chromium nitride formation. That again further confirms that we had higher plasma nitrating duration. So in short, I want to say that we have well confirmed this behavior, and then we propose the mechanism. Okay, due to the time lag, I can't discuss about the another interesting aspect, but I'll just simply show that. Here you can see that this peak, that is due to the carbon. Our process is a nitriding, but still carbon is picked up into the nitrided layer, that is in front of the nitrided layer. However, within the nitrided layer, we don't have any carbon content. We have almost zero carbon content, but carbon content is accumulated in front of grown interface of the nitrided layer. So there is some mechanism, but I will not discuss that due to the time constraint. But if you're really interested, I'll just show you this behavior. What happens is that during sputter clean duration, you got a carbon accumulation at the specimen surface. That can be from your furnace wall. You have that high temperature during sputter clean. That high temperature and adsorbed carbon and the oxygen into your passive film forms the CO gas. That CO gas is a direct contact with the specimen surface. That means you have the high temperature as well as carbonizing potential. That is enough to absorb the carbon at the specimen surface. Over a period of time, this carbon just simply pushed into the forward direction and the nitrided layer grows. So that is the mechanism what we have. So that's it. So this process is not really only to the laboratory level. People are just using this surface mechanical attrition treatment for commercial products as well. So just an example I shown here, this slide. So that's it. So these are our latest publication. If you're really interested, probably you can go through these publications, which are published in 2016. So thank you for your attention.
Thank you, Dr. Usmani. If you have any questions, we can take one question here.
So during this surface mechanical attrition process, will it lead to also mechanical alloying of the surface oxides into the substrate?
Yeah. There is a quite possibility. There is a possibility that, because see, in mechanical attrition you have the deformation. That means some amount of material is removed. It is again get welded. So that possibility is also there. That mechanism people have proposed. So in that case, there is a quite possibility of getting some kind of a mechanical alloying as well. So it can be trapped there.
Thank you.
Yeah.
Thanks, Dr. Usmani. It's a nice illustration of surface mechanical attrition treatment. I call upon stage now Mr. Slavomir Wozniak. He is the Managing Director of Seco Warwick Allied Private Limited. He is also in charge of their global facility in China as Managing Director. He is highly experienced in technical professional who has been with the Seco Warwick Global Group for many years. During his career with the company, he was responsible for development and growth of the company of various business segments within the group. Here is Slavomir Wozniak for us.